Let's take a look at the price of an exchange option. So in an exchange option, basically the payoff is that you get a max of VT minus UT or 0. UT is the asset you give up. So you are exchanging U for V. So if the price is V is greater than the price of U, obviously you will do the exchange. If the price of V is less than the price of U, this exchange option will have a value of 0 because you're not going to do that exchange. Suppose if both of them are both asset U and V are following a log normal process with a volatility of sigma U, V and sigma U, and let's say they have a correlation there. And suppose if, just to be general, that V and U, they all also paid continuous dividend at a rate of QV for asset V and QU for asset U, then we can under this construct we actually have a closed-form solution for the exchange option. Now we have to use the theory of equivalent martingale measures to do that. So by looking at it, we will see that if we will select asset U as the numeraire, basically the current price, let's say V naught divided by U naught, is equal to the expected value of VT divided by UT, where the expectation is given by with U being the numeraire asset. Now, if there's no dividend payment, there's no dividend yield, this part would not exist. Okay, and so in the example that we talked about earlier for the equivalent martingale measure, there's no dividend, and we basically have, in this case, V naught divided by U naught is equal to this expectation. Now, with continuous dividend payment, we have this extra term here. Now you can derive why that needs to be an extra term, okay? Now, using U as numeraire, again, you can derive another condition. So this is a condition between V and U, and here is a condition between the option price and U. So basically, the current price of the option divided by the current value of asset U really is equal to the final price, which is the payoff of the option, divided by the final value and maturity of asset U here. With this expectation is taken over U as the numeraire. Again, figure out why there's an extra term here, which is related to this, okay? Same approach, you will see that you only have one QU here. Now, once you have this condition here, again, for using equivalent martingale measure, in this case for the exchange option, you can rewrite this as, whatever is in the bracket is basically this VT divided by UT minus 1. So what have you done here? You basically created a payoff that is very similar to a call, where the strike is like $1. And if if V is following a log normal process and U is following a log normal process, the ratio V divided by U also follows a log normal process. And in that log normal process, your sigma square is really the sigma V squared plus sigma U squared minus 2 times the correlation rho times sigma V times sigma U. Since the ratio is also following a log normal process, and this payoff and this expectation value will then we have an expression directly for this, which is just really, we have seen that many times when we deal with the call price with the underlying asset following a log normal process. And here you can just basically treat this VT divided by UT as the value of a particular asset, right? And so it's like a call with this being the asset price and the call has a strike price of 1. So this really is the call price formula here. So you're taking this, so from an earlier condition here, we know the price of the exchange option is equal to initial price of asset U times this factor here and times this expectation, which we know the expectation is just the expected value of this thing here times ND1 minus K ND2, but K is 1, so just minus ND2. And then if we know this thing here, then we have a closed form solution. And we know the expected value of VT divided by UT is this. How do we know that? We know this condition by an earlier application of the equivalent martingale approach that we have seen here. So we just plug in what is expected VT divided by UT, which is this thing here. So you plug in this as this into this part here, you get this nicely looking closed form solution here. So essentially it is a solution of a call with a strike price of $1.